Hello everyone, Namaskar, welcome to Maths Guidance and welcome to the second lecture of chapter 10, that is circles. So far in lecture 1 we have gone through the terms, we have studied the terms related with the circles. That was the introduction part of this chapter. So we have studied the terms like chord, diameter, major arc, minor arc, segments, sectors like this. We have also studied the interior part of the circle, exterior part of the circle, and the circle itself. So that was lecture 1. So in this lecture, lecture number 2, we are going to study some properties of a circle, like the angle subtended by a chord at a point. One of the topics is this, and the second topic, the perpendicular from the center to the chord. And we are going to study two or three theorems related with these topics. So let's start the video, lecture number 2. Okay. So friends, let's start the topic. Today's topic, angle subtended by a chord at a point. Okay. So first of all, let us take a line segment like this PQ. This is a line segment PQ, and let us take a point R. Let us take a point R not on this line segment PQ. Okay. Let us join this PR and QR. So this is a chord. This is the line segment PQ. This is a point R. So there is an angle formed here. Okay. So what do you say this angle? This angle PRQ. This angle PRQ is called the angle subtended by the line segment PQ at the point R. Okay. Angle PRQ is the angle subtended by the line segment, is the angle subtended by the line segment PQ, at a point R, Okay. So this is the angle PRQ, angle subtended by the line segment PQ at a point R. Similarly, let us take a circle. Let us take a circle like this. This is a circle. Okay. And let us take a chord here. Chord is PQ. Okay. This is the chord of the circle. This is the center of the circle O. Let us join this PO and QO. Let us join this. Let us take a point here and a point here. That is, in the major arc we take a point, and in the minor arc we take a point. Okay. Let us name it R and S. Now let us join these points PR and QR. Okay. Let us join this also PS, QS. Now we see we are getting three angles. One is here, one is here, and one is here. So what do we name? Angle POQ. Angle POQ is the angle subtended by this chord PQ at the center O. Okay. Angle subtended by the chord PQ at the center O. Okay. So this is the angle subtended by this chord PQ at the center O. Similarly, angle PRQ. This is the angle subtended by the chord. Angle subtended by the chord PQ. At a point R in major arc. At a point R in major arc PQ. Okay. This is clear. Now there is one more angle, angle PSQ. This is the angle subtended by the chord. Angle subtended by the chord PQ. At a point S. In minor arc PQ. Point S in minor arc PQ. Okay. So these are the three angles, 1, 2 and 3. Now there is a relation between the angles and the length of the chords. Okay, suppose we are taking one small chord here, PQ. This is the center of the circle O, and we are taking a large chord here, PQ and RS. If you see the angle subtended, then you only looking at the figure, you can say that this angle ROS is greater. Angle ROS is greater than angle POQ. That means if your chord is longer, then the angle subtended at the center will be greater. Okay, so longer the chord, greater the angle subtended. Longer the chord, greater the angle subtended at the center, greater the angle subtended at the center. Okay, now what will happen if we take two chords of similar length, equal size? Okay, let us suppose this is center O, this is one chord, this is another chord. Let us suppose this is AB, and let us suppose this is PQ, and we are doing like this. So what about these two angles? There is a relation. We will come to that part. Okay, so we have to study this one, and there is a theorem related with this one also. So let's study that thing. Okay, now this is the figure I have drawn. Let us understand the relation between the angles subtended by the equal chords at the center. So basically, if you measure these angles, let us suppose this AB, CD and EF, these are equal chords of a circle. Okay, so if you measure these angles AO, B, COD and EOF, you find that all these angles are equal. Basically, angle AOB is equal to angle COD is equal to angle EOF. All these angles are equal if you measure it. So here comes the theorem. The theorem is like this, that equal chords of a circle, let us write it. The theorem is like this: equal chords of a circle subtend equal angles at the center. Okay, so the theorem is equal chord of a circle subtends equal angles at the center, equal angles at the center. Now we will prove this theorem. Okay, we will see the proof. Let us suppose this is a circle having center here, and these are the two chords. These are the two chords AB and CD. Okay, let us join these AO, BO, CO and DO. So we get two angles here. One is this and one is this. We have to prove that. First, what is given? Given is two chords AB and CD, AB equal to CD. Okay, these two chords are equal, AB equal to CD, and we need to prove that angle AOB equal to angle COD, that is the angle subtended at the center. Okay, now let's do it. Let's do the proof. So we will show that these two triangles AOB and COD are congruent. So let us take two triangles. In triangles AOB and COD. Okay, so these are all the radii of the circle: OA, OB, OC and OD. So OA equal to OC we can write, OA equal to OC, and OB equal to OD we can also write, OB equal to OD we can write. These are the radii of the circle. Okay, now 1, 2. Third one is this AB equal to CD. It has been given. AB equal to CD, it is given that these chords are equal. Therefore, by SSS congruence, SSS congruence rule, we can say that triangle AOB is congruent to triangle COD. Okay. Now by CPCT, we can easily say, that angle AOB is equal to angle COD. Corresponding parts of, I hope you remember this one, corresponding parts of congruent triangles. Corresponding parts of congruent triangles. Okay. So this one is also proved, that the angles subtended at the center by two equal chords are always equal. Alright. Now we will see that its converse is also true. Okay. First of all, the theorem is equal chords of a circle subtends equal angles at the center. Okay. And we have seen the proof. It's a very simple proof. These are the radii of the circle. So OA equal to OC, OB equal to OD, and this is given AB equal to CD, equal chords. So by SSS, two triangles are congruent, and by CPCT, these angles are equal. Now let's see its converse. Okay. So this is the converse of this theorem. The theorem was equal chords of a circle subtends equal angles at the center. The theorem converse will be like this: if the angles subtended by the chords of a circle, at the center are equal, then the chords are equal. Okay. So let us prove this one also. It's a simple proof. Let's do it. Suppose this is the circle. This is the given circle, and this is the center. These are the two chords. Let us join this. These are the angles subtended at the center. Okay. This is AB and this is CD. So we have to prove that these chords are equal, and given is these angles subtended by the chords of the center are equal. Given is these angles are equal. So given, what is the given thing? Given is angle AOB is equal to angle COD. And what we need to prove? Is length of chord AB is equal to CD. Now let's see the proof. In the similar way, we will do it in triangles AOB and COD. What we have? OA equal to OB, OA equal to OC, and OB equal to OD. Okay. And angle AOB, that is given, equal to angle COD. These are the radii of the circle. And this is given. Now by SAS, okay, by SAS, side angle side congruence rule, we can say that these two triangles are congruent. Triangle AOB is congruent to triangle COD. Now by CPCT, we can say that AB equal to CD, the third side of the triangles AB equal to CD. Now this is what we have to prove. Means if the angles subtended at the center of a circle by the chords, two chords are equal, then these two chords are also equal. This is the converse of the theorem which we have studied here, that equal chords of a circle subtends equal angles at the center. This is the theorem, and this is the converse. If the angles subtended by the chords of a circle at the center are equal, then the chords are equal. Alright. So now these two were the important proofs of this topic. Now let's move forward. Alright. So friends, let's understand this topic: perpendicular from the center to a chord. Okay. Let us suppose this is a circle. And this is a chord AB. Okay, this is a chord AB. This is the center O. So let's do an activity. The activity is like this: that you have to, the activity is like this, that you have to draw this circle on a tracing paper or a thin paper so that folding and tracing can be done. So draw a chord AB, the center O. Alright. Now fold the paper along a line through O like this. Fold the paper along a line through O. If you fold like this, okay, like this, you will find that this B is coinciding with A. This B is coinciding with A, and it totally covers it. Okay. And when you measure the angles, these angles, let us suppose this is point M, angle OMA and angle OMB, you will find that angle OMA is equal to angle OMB, these two are equal, and that is equal to 90 degree. Okay. So that means this OM is, you can say that this OM is perpendicular to AB. Okay. You will also get to know that this MA is equal to MB. If you do this activity on the tracing paper, you will get to know these things. So here comes our theorem. The theorem is coming from here. The theorem is like this, that the perpendicular drawn from the center of a circle to a chord bisects the chord. This is the perpendicular drawn from the center of a circle to the chord. Okay, let us write it. The perpendicular from the center of the circle, to a chord bisects the chord. So we will prove it. What are the given things? Given is, let us draw another figure for it. Let us suppose this is the figure. This is the chord AB, this is the center O, and this is the perpendicular. Okay, this is the perpendicular, this is the point M. Now given is that OM is perpendicular to AB. Okay, center of the circle is O and chord is AB. Center is O, chord is AB. These are given things. Okay. Now what we have to prove is this MA bisects the chord, means MA equal to MB. MA is equal to MB. We have to prove. Now let's prove it. So first join these things, OA and OB. Join it. Okay. So in triangle OAM and OBM, we have OA equal to OB. This is the radius of the circle. Okay, radii. OA equal to OB. Now OM is the common part. OM equal to OM is the common part. We can say it is the common part. And this angle OMA is equal to angle OMB. It is given. Okay. Now we can say these sides are equal, this side is common, this is. So by RHS also we can say, by RHS, congruence rule. That is right hand side, right angle, hypotenuse and side. Right angle, hypotenuse and side. We can say that triangle OAM is congruent to triangle OBM. We can say this. Now having said this, it means by CPCT we can say that MA or AM is equal to MB or BM, and this is what we have to prove. MA, what we have to prove? MA equal to MB. Okay, MA equal to MB proved by CPCT, corresponding parts of congruent triangles. So basically the theorem is the perpendicular from the center of the circle to a chord bisects the chord. This is the perpendicular from the center of the circle and this is the chord AB. It bisects the chord. That means MA equal to MB, which we have to prove. So let's join this OA and OB. So OA equal to OB, the radii of the circle, OM equal to OM common, and OMA equal to angle OMB right angle. So by the RHS congruence rule, these two triangles are congruent. So by CPCT, MA equal to MB, it has been proved. Now let's see the converse of this theorem also. Okay, it has a converse also. Let's see it. So friends, this is the converse of the theorem. The converse is like this: the line drawn through the center of a circle to bisect the chord is perpendicular to the chord. Okay, so let's draw the figure here also. It will help us to understand, it will help to visualize us. So let us suppose this is the center and this is the chord AB. So the line drawn through the center of a circle to bisect a chord, that means it is bisecting the chord. Let us suppose this is M. Now we have to prove that this line is perpendicular. Okay, so we will see the proof of this theorem. First of all, what are the given things? So the given things are bisect the chord is perpendicular to bisect, means MA equal to MB. We have been given MA equal to MB because this line is bisecting the chord. Okay, the line is bisecting the chord. You can write it here. The line is bisecting the chord. Okay, so MA equal to MB we have been given. So what we have to prove? To prove is angle OM is perpendicular to AB, or you can say that angle OMA equal to angle OMB equal to 90 degree. This is what we have to prove. Now let's see the proof. Similar process we will apply in let us first join these two radii. Okay, so in triangles OAM and OBM, what we find that OA equal to OB, radii of the circle. Okay, radii of the circle, OA equal to OB. Now OM equal to OM, this is common. OM equal to OM, it is common. And the third one is this MA equal to MB. This is given. Okay, so this is common. This is the radius and this is the given thing. So basically by SSS rule, we can say that triangle OAM is congruent to triangle OBM. Now by CPCT we can say that angle OMA is equal to angle OMB. We can say that, but till now we cannot say that these two angles are equal and 90 degree, because we will have to do another thing, that this is a linear pair. Now we can say that angle OMA plus angle OMB is equal to 180 degree. This is forming a linear pair. Now since these two angles are equal, that means twice angle OMA or twice angle OMB is equal to 180 degree. This implies angle OMA or angle OMB, that is equal to 180 by 2, that is equal to 90 degree. Therefore angle OMA equal to angle OMB equal to 90 degree, or OM is perpendicular to AB. We can say OM is perpendicular to AB. Now this is proved. Okay, so the converse, the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. If this line is bisecting this chord, then this is perpendicular, okay, to the chord. So given MA equal to MB, we have to prove that OM is perpendicular to AB, or these two angles are 90 degree and are equal. So in these two triangles OM and OBM, we have proved that by SSS rule these two triangles are congruent, and by CPCT these two angles are equal. Now by linear pair we can say that these two angles are actually equal to 90 degree. That means this OM is perpendicular to AB. Okay, now let's move on. So guys, this was lecture number 2 and we have studied two topics. The first one was angle subtended by a chord at a point, and we have seen two theorems. First one was equal chords of a circle subtends equal angles at the center. This was the theorem and we have seen its proof. And the converse of this theorem, that if the angles subtended by the chords are equal, then the chords are equal. Alright, this was the first topic we have gone through today's videos. Second topic was perpendicular from the center to a chord, and we have seen through an activity and then to the theorem that the perpendicular from the center of the circle to the chord actually bisects the chord. Alright, and we have seen its converse also, that the line drawn through the center of the circle to the chord actually of a circle to bisect a chord is perpendicular to the chord, and we have seen its proof also. So these are the topics we have discussed in today's video. So let's conclude this lecture here only, and we will move on to another topic in the third lecture. Alright, so thanks for giving your time. Thanks for joining me. Keep watching my videos. Thank you very much.